Today we'll see about logical operations. Like first of all, before going to see what are the logical operations, first of all, we need to know what is meant by statement. Okay, how we can define a statement. Suppose um, I will tell this statement like, do you speak English? Is it statement means do you speak English? We cannot say whether it is true or false. Then it cannot be considered as a statement. On the other hand, you consider other statement, other sentence like the earth is round. Here we can say this particular sentence is true. So we can consider it as the statement. Similarly, you consider 2 plus 3 equal to 5. For this also we can say the state this particular sentence as true, so it can be considered as the statement. Got my point? Suppose if I tell 2 plus 2 equal to 5, can we consider it as statement or not? 2 plus 2 equal to 5. Yes or no?
Yes, sir.
Yes, right? 2 plus 2 equal to 5 is false. So if you could able to say whether it is false or true, then we can consider it as statement. So coming to the definition, statement of a proposition is nothing but a declarative sentence that is either true or false, but not both. For example, I will say x is equal to x or x minus 3 equal to let us say 2. X minus 3 equal to 2. Can we consider it as a statement? X minus 3 equal to 2.
No, sir.
No. Why? Because we don't know whether it is true or not. Right? So, I think you have understood what is the definition of statement. It is a sentence that can be that can have truth value either as true or false, but not both. That's the definition. Okay. Several other examples also given in this. Just you consider this particular one. Take 2 aspirins. It is a command. It's not a statement. Take 2 aspirins. Suppose a doctor has told this one. Then you cannot judge whether it is true or not. Okay, just it is a command. And question, like earlier we have seen, do you speak English? This is a question. Okay, it is also not a statement. Similarly, here we have seen 3 minus 6 is equal to 5. This is also not a statement. Why? Because we cannot say whether it is true or not. Okay, these are some of the examples. And coming to the logical connectives, like if you have two statements, let us say P and Q. These are the two statements. We can connect these two by using some of the logical connectives. Okay, one of those is and. What we call this? Conjunction, right? Conjunction. Similarly, for the same two statements, we can use disjunction, that we can say it as or. And is one logical connective, another one is or. Okay, this we call it as conjunction, this we call it as disjunction. Okay, as you know, I think you might have learnt this one in 10th standard itself, that what is the truth table for conjunction P and Q? P and Q. Suppose
True and
P is,
true is true, remaining are false.
yeah, if both are true, then only this conjunction is true. That is P and Q is true. Otherwise, it is false. So remaining all cases. How many cases will be having remaining?
3 cases.
3 cases. Okay, like true, 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 false, false, true, false, false. So for all the 3 cases, the output is false. So this is about conjunction. Next, coming to disjunction, whenever both are false, then only outcome is false. Otherwise, it is true. That is, if one of the statement is true, that is sufficient to claim that PRQ is also true. Okay, that is about the truth table that we will see anyway. Next, coming to special type of operation called negation. Negation, suppose a statement P is there, negation P in the sense reverse to it. Suppose we'll say the sun is shining today, this is P. Then what can be negation P? Sun is not shining, is not shining today. Like that we can negate it. Suppose the truth value of P is true, then negation P will be false. If the truth value of P is false, then the negation P will be true. So this is another what you call logical operation that we can perform, but it cannot be considered, this negation cannot be considered as the logical connective. Why? Because it is not connecting any two statements, just on one particular statement only it can be operated. Got it? Negation cannot be considered as logical connective, but it can be considered as logical operation. Okay, logical operator we can say negation. Whereas this and or, okay, these two are logical connectives. Why? Because it is connecting both the statements. It is connecting both the statements. Okay, that's why these are logical connectives. This is just a logical operation operator. Clear? Yes. So same points no, what you call mentioned in this slide as well. This negation we will denote with the symbol tilde. Okay, that operator we call it as a tilde operator. Next, you consider of course these are the examples. P is 2 plus 3 is greater than 1. What is the truth value of P? What is the truth value of P? 2 plus 3 is greater than 1. Truth value of P is true. Why? Because 5 is greater than 1. 2 plus 3 is 5. 5 is greater than 1. So it is true. Negation P should be false, isn't it? Negation P should be false. And so here we are having greater than. So what can be negation? Less than or equal to. Here we are having greater than symbol. So negation P will contain less than or equal to. Now you consider 5 is less than or equal to 1, which is nothing but the truth value of this one is false. Clear? Yes, P and negation P, clear? Yes, please respond, ma'am.
Yes, sir.
Yeah. Next, of course, conjunction we have seen, and disjunction we denote with or. And the truth table we can say truth table here like this: P and Q. Whenever both are true, then only it is true. Whenever both are false, then only it is false. In all the remaining cases, it is true. In all the remaining cases, it is false. So this is just truth tables. Next, coming to the compound statements, in the sense whenever we have only two statements, okay, P and Q, okay, in general we denote these statements in with capital letters in general. Okay, there is no restriction, but in general. Now P and Q, if you write, just we are connecting two statements. If you have more than one, more than two, sorry, more than two, then we can consider it as compound statements. P and Q is one statement. Okay, if you put any other statement like R, you can choose. Okay, P and Q R, R, or P and Q and R, like that. If you use another statement as well, then we can consider it as compound statement. Or you even sometimes with two statements also, whatever we will be getting, that is P and Q can be considered as the statement again, and this can be compound statement. This is a single statement, this is single statement, P and Q will be compound statement. Got it? Now you can consider compound statement as like this as well: P and negation P. What does it mean? We are performing conjunction between P and negation of itself. Okay, that is also quite possible. So in that particular case, how many entries will be there in the truth table? Like here we are having 4 entries, right? 4 rows. Like that, P and negation P, how many entries are possible? Suppose P is there, negation P is there. If P is true, yeah, true, then it will be false definitely. If it is false, then it will be true. Okay, now you try to write what is the truth table for P and negation P. Okay, P and negation P. What is the statement? Whenever we have both the truth values, both the statements as true, then only the resultant is true. That is with respect to end. Here you can observe. So true and false we will get true and false will get false. Similarly, false and true will be getting false. Okay, if you observe in the right hand side, what you call rightmost column, this is having all the entries as false. Such kind of compound statement we consider as any answers? You consider it as contradiction. Contradiction. Whenever we have truth table entries in one particular column entirely as false, then we can consider that one as contradiction. That particular compound statement as contradiction. On the contrast, if you have both the values as true, if you have entire column as true, then we can consider it as tautology. Okay, that we will see anyway. Just I am trying to give some intuition here itself. Suppose you consider P or negation P. P or negation P. If P is true in general, just without considering any what you call table and all, just you consider P is false, let us say, then negation P will be true. If P is true, then negation P will be false. So definitely one of these will be true. So ultimately P or negation P will give always true, isn't it? So whenever we have in the truth table entire column as true, then always one particular compound statement is always true means that we will consider as tautology. Whenever one compound statement is false always, then we can consider it as contradiction. Clear? Yes. Yes, do you have any doubts? Okay, yeah, this is one of the examples for compound statement. Here we are having P and Q are negation P. So how we can write the truth table for it? First we need to have P Q, then P and Q, of course this one up to this, then negation P. Next P and Q are negation P. So P and Q we know already, whenever both are true then only it is true, remaining all will be false. This is fine. Next negation P. In general P and negation P only if we have, then we will be having only two entries. But here we need to consider that with respect to this P. Okay, here we are having for P four values. Okay, four truth values. That's why correspondingly we are having, although distinct values are true and false only, but we need to write corresponding to P, this particular P, what is it? Why? Because here we are considering P and Q are negation P. So P and Q, what is the negation P at this particular point? Whenever it is true, what is negation P, that we have to consider. In this particular one, what is negation P means, P and Q we have considered true and false. Okay, P, in this P and Q we have considered true and false. Corresponding negation P only we have to consider. That's why we are having four entries here. And I hope you understand why we are having four entries for negation P. In general, P negation P earlier we have considered, right? How many entries we have considered? Only two entries. But why we are having here four entries is like here P and Q is containing four entries, and now we have to perform P and Q or negation P. P and Q or negation P. So while considering this particular operation, whatever the P we have considered in the first P and Q, that P negation P only we have to consider. Negation of that P only we have to consider. That's why we are having four entries here. Clear? So true, here we are performing disjunction, okay, or operation. Whenever both are false, then only it is false. Remaining all entries will be true. So this is the truth table for compound statement. Is it clear? Yes. Yes, if you have any doubt, you ask me.
Clear, sir.
Yeah. Next, coming to the important notion called quantifiers. Quantifiers, in the sense, earlier we have considered the statement as like P will be there. Okay, we will say that statement and the truth value as true. What does it mean? This statement is true for all the instances. Like you consider um, okay, you consider sun rises in the east. Okay, that is true, that is having the truth value as true. So always it is true. But if you give a statement which can be true for certain values but not all the values, then we can specify the by using the what you call notion called quantifier. I'm repeating once again. I will say the statement. Okay, that statement is true for certain values of certain values only. Okay, then we can use quantifier. For example, I will state the statement. Okay, I will tell you the statement. That statement is true for all the values in all the instances. That statement is true. Then that also we can specify by using quantifier. Okay, there exist two type different quantifiers in general. Okay, two different quantifiers. Those are, one is used to indicate for all the instances. For all the instances, the given statement holds the truth value. Okay, whether it is true or false, that is secondary, but for all the instances it will hold. Okay, for certain instances only it will hold, in the sense specified values are for certain values. For some values we can say, then that is second quantifier. For all we will denote with this symbol, for all. Understand? Next, for some, in the sense, we will denote like this: there exist. Okay, this is the symbol to denote for some, like there exist. We call it as there exist. This we call it as for all. Okay, when we will use this for all quantifier is for all the instances, for all the values for all the allowed values, it is it holds the same truth value. Here for some specified values, okay, then only the truth value holds, then we can say there exist. Understand the difference? When we will use for all, when we will use for some, when we will use there exist. Yes, we will see examples, don't worry. Any doubt at this point? Yes, any doubt, ma?
No, sir.
Okay, see here, for all, first of all we'll see for all. This we can consider it as universal quantification of a predicate p of x. Universal quantification. Okay, here we will denote like for all x p of x. That is, for all the values of x, p of x holds, p of x is true. That is the meaning of this. Okay, for all values of x, p of x is true. That we will denote with for all x, p of x. Okay, and this we consider as universal quantifier. Okay, now let us see the example, like mm, for all x, p of x, we will say what is p of x is, p of x is predicate, like you consider yeah, any other example we'll see. Yeah, you can consider this example: minus of minus x is equal to x. For all the values of x, this statement is true. Yes or no? For all the values of x, you can put 1, you can put 2, 3, 4, or 1.1, 1.2, anything you put as the value of x, minus of minus x will be x. So for all the values of x, this is true, right? So how we will denote that? By using for all x p of x. Okay, that is the use of universal quantifier. Clear? And you consider here x plus 1 less than 4. X plus 1 less than 4. Can we consider it as for all? Can we put for all x q of x? What does it mean? For all the values of x, q of x is true. Suppose if you put x value as 1, then it is fine. If x value as 2, then also it is fine. X value as 0, then also it is fine. But x value, if you put it as 3, then is it true? X value as 3, then 3 plus 1 is 4, 4 less than 4. Is it true? No. So what we can say, can we consider for all x q of x in this particular example? No. Why? Because for all the values of x, this predicate is not what you call holding the truth value. That's why we cannot say for all x in this particular example. Whereas minus of minus x, this particular predicate is always true for all the values of x. So we can use for all x. So in this particular case, what can be used is we can use second quantifier called there exist. There exist x. Okay, there exist x, and we can say q of x. What does it mean? For some values, at least one value of x, this q of x is true. Yes or no? For x, at least one value for x exists or not? Yes. What are the values? Can you tell where q of x is true? For which values q of x is true?
1, 2, 3.
Yeah, 3. No. For 3, it is not true. 1, 2, it is true. Yeah. So yeah, correct. Minus infinity to 2. Up to 2, it is fine. But after 2, we cannot say it is true. So there exists at least one value where q of x is true. So we can say there exists. If at least one value exists, then we can use this quantifier. Okay. So this is a second quantifier, and we will call this one as existential quantification. Okay. And now this we can denote as there exists x p of x. That means at least for one value of x, p of x is true. Okay, we can say there exists a value of x for which p of x is true. That we denote with there exists symbol. Clear? Next, coming to the ordering, now you consider we are having two variables in the predicate. Okay, p of x comma y, p of x comma y, and if we have for all x, for all y, you can write it in any order, like for all x, for all y, for all x, for all y, for all x, both are same. Why? Because for all the values of x, for all the values of y, p of x comma y is true. Understand? For all the values of x, for all the values of y, p of x comma y is true. So for all the values of y and for all the values of x, p of x comma y is true. Like that, we can say in other way as well. So order does not matter. In any order we can use. If you have only for all symbols, only for all symbols if you have, then we can say in any order the truth value is same. Understand my point? For all x, for all y, for all y, for all x. Or you consider three variables we have for all x, for all y, for all z. Here we can write it in any order for all z, y, for all x. Like that, in any order we can use these what you call universal quantifiers. Clear? Yes, if you I'll show you the example, then you can understand in more better way. Next, consider this existential quantifier is nothing but there exist. Okay, if we have only there exist, like earlier we have there exist, what you call, for all x for all y. If we have only there exist, like there exist x, there exist y, p of x comma y, this can be equivalent to, yeah, now you please tell me, this can be equivalent to there exist y, there exist
X.
x, p of x comma y. These two are same. That means if you have only one quantifier, either universal quantifier or existential quantifier, order does not matter. Okay, you can write it in any order. But on the other hand, if you have combination like one for all symbol, that is for all x, there exists y, p of x comma y. What does it mean? What is the meaning of this one? For all the values of x, what's the meaning of this? For all the values of x, there exists some y where p of x comma y is true. I'm repeating once again. Try to understand the meaning first. For all x, that means for all the values of x, there exists some y for, such that p of x comma y is true. Okay. On the other hand, if I write like this, there exists y for all x, p of x comma y. What does it mean? For some values of y, okay, for some values of y, and we can consider all the values of x. Okay, only for some values of y we can consider any value of x, p of x comma y is true. Okay, are these two same or not? This is a question. I think you have got the question at least. I'm not expecting the answer. Just try to understand what is the meaning of there exist. For all x, there exists y. What does it mean? For all the values of x, there exists some value of y such that p of x comma y is true. Okay, there exists y for all x means for some values of y, and for any value of x, we can say p of x comma y is true. Are these two same or not? We will see. Okay, with some explanation you can understand this. Yeah, I think you have got the question. Yes or no?
Yes, sir.
Yeah. Now applying both universal and existential quantification, like you consider for all a there exists b. Okay, this is the statement. Like p of x comma y I have told, right? Like p of a comma b. What is a comma b? P of a comma b is nothing but a plus b is equal to some integer. Okay, now you consider what is the meaning of this. For all a there exists b. For every a there is a b such that a plus b is equal to in. Like you consider any value of a. Okay, a can, you consider any value of a, like 5 or 10 or 15 or -5, anything, and you can add some value of b and you will get this particular number. Is it true or not? Let us consider this as a 10. Okay, and you can choose any integer here. In is 10, any integer here, like you can choose 5, you can choose 10, you can choose -5, you can choose -15, like that. Let us consider this as 5. So there exists b or not? In order to make it as a true value, like 5 plus 5 is equal to 10, we can make it as true. So there exists b. Yes or no? Yeah. Similarly, you consider -5, then we can consider 15 as the b value, right? -5 plus 15, we will get again 10. So for any value of a, we can give b, okay, such that a plus b is equal to that in. So this is the understanding of for all a there exists b. Now you consider there exists b for all a plus b is equal to in. So what we can consider, there exists b such that for all a plus b is equal to in. That means I will say some values of b like -5, 15 or 10, any value you consider. Okay, there exists some value. Can we add any number so that we will get 10? Try to understand the meaning. Here there exist some values I am saying. Okay, you can take any numbers here, but a value, what is the quantifier before a? What is the quantifier we have before a?
All belongs to A.
Yeah, that means for all, right? For all a. So any value of a you consider. Okay, any value of a we can take. By adding these two we should get 10. So if you take -5 only one value for b, there exists means at least one value, so you consider -5. So -5 with any value, if you add, is there any guarantee to get 10?
No,
Any
sir.
value in the sense, you can take any value. You can take 10, you can take 15, you can take 0. For all the values this should be true. Why? Because for all a is the quantifier. For all is the quantifier before a. So is this true or false?
False.
False. Definitely it is false. Why? Because for any value we cannot add uh, what you call, we cannot guarantee that for all the values we will get 10 only the sum. Only for one value we will get sum as 10. But what is the quantifier before a? For all. So the statement is always false. Now you judge whether these two are equal or not. This is one statement, that is for all a there exists b. Here we are having same statement, but quantifiers are in different order. There exists b for all a. Whether these two are equal or not?
Not equal, sir.
Not equal. Understand? Yeah, this is the answer. Yeah, coming to the previous one, there exists y for all x p of x comma y. For all x there exists y p of x comma y. Whether these two are equal or not? Now you answer.
No, sir. Not equal.
Yeah, those two are not equal. Yeah. Next. Yeah, even we can apply there exist or for all operator for negation of one particular statement as well. Earlier we have seen for all x p of x comma y, and a negation is also, negation also we can apply for this particular statement. Okay, I think with this we can stop this particular what you call conjunction, disjunction and quantifiers, and now we will see this implication. You know the implication, right? Like conditional statements. Like we will be having two statements. p if p is true, then q is always false. If p is true, then q is always false. Okay, that is implication. If p is true, then q will also be true, and we will denote that with p implies q. Yeah, now you consider p implies q. In this particular one, p is called as antecedent or hypothesis. P is called antecedent or hypothesis, and q is called consequent or conclusion. Consequent or conclusion. You remember like this: antecedent implies consequent, hypothesis implies conclusion. Hypothesis leads to conclusion. If hypothesis is true, then conclusion is true. Conclusion is true. Similarly, antecedent is true, then consequent is true. Okay, now you can consider the example. P is I am hungry, q is I will eat. So if I am hungry, I will eat. That is the statement. Okay, so p implies q is we will use in that particular context. Whenever p is true, then q is also true. Or we can read it as if p then q. If p then q. What does it mean? If p is true, then automatically q is true. That's what the meaning. Yeah. Now consider another two set of statements, like P is it is snowing, Q is 3 plus 5 is equal to 8. Okay, in general, there is no link between P and Q. But if you write P implies Q, okay, logically it is not logical. Sorry, what you call it? Intuitively, there is no link between P and Q. Yes or no? It is snowing. It is independent. 3 plus 5 is equal to 8. It is independent. But if you write P implies Q, logically we are making these two as connected. Okay, although those are not related in real time, we can connect these two statements by using this logical connective called implies. Okay, this we can consider call it as implies, like or and symbols or negation we have here, we are having implies. Okay, next what is the truth table for this? Yes, what is the truth table for this? Whenever we have P as true, definitely definitely Q should also be true. Understand? If Q is true, then it is fine. It is what you call following the rule. Why? Because if P, then Q. If P is true, then Q should be true. So if it is satisfying, right? If P is true, Q is also true. So P implies Q will be true. On the other hand, if P is true, Q is not true. Okay, which is not allowed. That's why we are having false here. Understand the understand why we are having true false is false. Why? Because if P is true, then Q is false, then it is not allowed. That's why P implies Q is false. Next, if P itself is false, then Q can be anything, and P implies Q is true only. That is the what you call fundamental operation of implies is following here. Whenever P is true, Q should be true. That is the restriction. Okay, that is the requirement. So that requirement is satisfying in the first statement. Okay, first combination. In other things, in the second one, it is not following. That's why it is false. In other two, P itself is false. So irrespective of Q value, the resultant is true itself. Why? Because P implies Q we are following, right? We are obeying that particular condition. Understand my point? Yes, shall I repeat once? Yes, did you understand why we are having true false only, false remaining all as true? Yeah. Okay, now you consider these are examples. You can go through this. I'll share this PPT. Next, yeah, important notions called converse. Suppose P implies Q is there. For the implication only, we will be having three types of things. P implies Q is the implication. For this, what is the converse? Converse is nothing but just we will be having Q as the first statement. If Q, then P. This is converse. If Q, then P. That is converse. Next, inverse in the sense we will be having negation P implies negation Q. That is inverse. And there is one important notion called contrapositive. Contrapositive is nothing but negation for P implies Q itself. For this P implies Q only, contrapositive is nothing but negation Q implies negation P. Okay, these are the three things. First one is what? Converse. Next one is inverse. Next, contrapositive. Okay, this contrapositive is very, very important. Why it is important is just you tell what is the truth table for P, Q. We can consider in the previous slide itself. Yeah. Yeah. Now you consider same P and Q. Okay, I will write here. mm, Q implies P. What is Q implies P, ma? It is called as hmm, Q implies P. What we call this? Q implies P is called as converse. Okay. So now what is the truth table for Q implies P? Please tell. For Q implies P, truth table. Hmm. Yes, please answer, ma. Yes, Maruti.
Sir,
Yeah, please answer. Q implies P. What is the P implies Q truth table? Just whenever we have first value as true, second value as false, then only the resultant is false. Okay, remaining in the remaining all cases it is true. So in the same way, first statement is Q. So this is true. Okay, and the P should be false. Then only the resultant is false. So true, true. Okay, the resultant is true. False, true. What we will get?
True.
True. Then next, true, false. Whenever we have true, false, then we will get false. False, false. Of course, it
False.
will be true.
True.
Yeah. Now you consider negation P implies negation Q. You tell me. Negation P implies negation Q.
True.
Okay. First one is true. Why? Because both will be false. Next,
False.
false. Here
No,
you
sir.
see
True.
true. Why? Because negation P is false. Negation Q is true. So it is true. Next, negation
False.
P becomes true. Negation Q becomes false. So it is false. Next,
True.
true. Yeah. Next, consider contrapositive. What is contrapositive for P implies Q? Negation Q implies negation. Negation Q implies negation P. This is the contrapositive for P implies Q. Now you say what is the negation Q?
True.
False, and if we have false for the first one, definitely it will be true. Okay. Here we are having true, and this one becomes
False.
so true, false. What we will get?
False.
False. Next, here it is false. It will become false. So automatically it will be
True.
true. Next,
True.
it is also true. Now you consider this particular column. This particular column. Is there any similarity?
Total similarity.
Yeah, same. So P implies Q is nothing but negation Q implies negation P. That's why this contrapositive is having that importance. That article. We will see how what is the application for considering this contrapositive. Why we are what you call putting extra attention on this particular contrapositive. That you will come to know in coming classes. Just you remember, P implies Q is equivalent to its contrapositive. What is the contrapositive? For P implies Q, contrapositive is negation Q implies negation P. Clear?
Yes, sir.
Yeah. Next, yeah, these all you have understood here. Like if it is raining, then I get wet. Converse is if I get wet, then it is raining. Like what is P? It is raining. What is Q? I get wet. Okay, if then these are just implication. Now how we will write converse? Q implies P. If I get wet, then it is raining. Next, what is contrapositive? If I negation Q, right? What is negation Q? I don't get wet. So that is negation Q. If I don't get weight, then it is not raining. That is negation P. It is not raining is negation P. Is it clear? So this is about implication, converse, of course, inverse also we can write. Then contrapositive. Yeah. Next, equivalence are biconditional. Biconditional in the sense we have seen implies, right? That is if P then Q. That's what we have seen with respect to implies. If P then Q. Suppose if Q then P. If Q then P. Can you able to follow? If P then Q. This is true, and if Q then P. This is also true. Then we can consider as P if and only if, that we can write it as if, like this, if and only if Q. What does it mean? If P then Q, if Q then Q, then P. Okay, these two statements are true. Then we can say P if and only if Q. Yeah, any doubt, ma? Okay, here you see P if and only if Q. Okay, in short we can write it as IFF. If and only if can be written as IFF. What is the meaning of this? If P then Q, if Q then P. Okay, this we can consider as biconditional or equivalence. Okay, what's the truth table for this? Is just if you write it like P Q, then what is the internal meaning? P implies Q should be true, and Q implies P is also should be true. Yes or no? So we will write P Q, then we can write it as P implies Q. Okay, and Q implies P also we will calculate. And if P implies Q is true and Q implies P is also true, then the resultant, that is P by implies Q, is also true. We will denote with this symbol. Okay, now you answer what is P by implies Q. Yeah, P by implies Q is nothing but whenever P implies Q is there, Q implies P also should be true. What does it mean? P implies Q should be true and Q implies P also should be true. Okay, this is the equivalent. Now can you able to write the truth table for P by implies Q? We know P implies Q truth table. We know Q implies P truth table as well, we can write. So what is P by implies Q? Is nothing but P by implies Q is nothing but, in general, what is P implies Q? You please tell. True, false, second one will be false, then remaining will be true. Yes or no? This is the truth table for P implies Q. Next, what is the truth table for Q implies P? Earlier we have seen Q implies P. What is the truth table?
True, true, false, true.
True, true, yeah, true, true, false, true. Yeah. Now you apply P by implies Q. That is end operation. Conjunction will apply. So true, true means what is the resultant? End operation.
True.
True. Next, false, true. Just end operation.
False.
False. Next, true, false.
True.
True, false.
False. False.
False. Next, true, true.
True.
True. So this is the truth table for P by implies Q. Clear?
Last one is true.
Yeah.
False. True, true.
Last
repeat.
one, here we are having true and true, right?
Yes.
Yeah, here you can observe. See, P implies Q is this. Q implies P is this. Now we are applying end operation between these two. Okay. True here, true here. So what is the resultant? True. Next, true here, false here. So the resultant is false. Next, false here, true here. So the resultant is false. Next, true here, then the resultant is
True.
true. Yeah. So sorry, this is true. Yeah. So this is by implies q. Here, just spare for 2 minutes. Yeah, this is the truth table for P by implies Q. Next, like this, we can compute the truth table of the statement. Yeah, this is one of the examples. P implies Q, by implies negation Q implies negation P. Just we will substitute, right? P implies Q, we know. Negation Q we can write. Negation P we can write. Negation Q implies negation P also we have seen earlier. This is equivalent to P implies Q only, right? Why? Because it is contrapositive, right? P implies Q, contrapositive is negation Q implies negation P. Next, now we have to apply by implies. When how we can calculate by implies is whenever both are true, then only whenever both are true or both are false, then the resultant is true, otherwise it is false. Now you consider P implies Q, that is this one. Next, negation Q implies negation P. Of course both are same, right? So definitely we will get all values as true. Whenever both are true or both are false, then the by implies will give true. So automatically we will get all values as true. Whenever we get in the truth table all values as true for any column, then we can consider that statement as I have told you. What is it? Tautology. Clear? So whenever we have this kind of thing, then this statement, this compound statement, we can consider as tautology. Whenever we have all the values as false, then yes, please respond, ma. If all the values as false, then we can consider it as contradiction. Okay. So yeah, in the next one it is there. A statement that is true for all of its propositional variables, it is called tautology. Okay. If the statement is false for all the values of all the propositional values, then we can say it as contradiction, or another name is absurdity. Okay, absurdity. Next, if a statement is not a tautology, this is very important question in competitive exams as well. Try to understand here. If the statement is not tautology, and of course it is not contradiction as well, then we can consider call it as contingency. Okay, contingency. Yeah. A statement can be either true or false depending on its propositional variables, is called contingency. In other words, we can say a statement which is not tautology, which is not contradiction, is called contingency. Okay, this is one of the examples for tautology. And P and negation P, which we have seen earlier, that is absurdity, that is nothing but contradiction. And this you can consider as it as contingency. Why? Because it is not a tautology, it is not a contradiction or absurdity. That's why it can be considered as contingency. Okay, this is one of the examples. Here you can consider, you can observe here true and false, both we are having. So it cannot be a tautology, it cannot be a contradiction. So we can consider it as contingency. Clear? Yes?
Yes, sir.
Yeah. One last point here is we say two statements as logically equivalent whenever both the truth tables, okay, both the truth tables as the same. Like earlier we have seen P implies Q is similar to negation Q implies negation P. Both are logically equivalent. Okay. These are some of the other examples. P implies Q is equivalent to negation P or negation Q. This we have to show. How we can show? Just we will find the truth table for P implies Q, and we will find the truth table for negation P or negation Q. And if you observe this, if you perform by implication operation in between these two, then we will get tautology. Then we can say those two as equivalent. Okay, or in other words, we can say truth tables are same. True, true, false, false, true, true. Next, true, true. Okay, truth tables are same for negation P or negation Q and P or Q. Okay, this can be observed. Okay, this can be what you call determined by performing by implication as well. When we perform by implication, we will get tautology. Okay, this is a important property. P implies Q is nothing but negation P or negation Q. This is very, very important one. Next, of course, this also we have seen, and the method of showing both these statements as equivalent is different. Just earlier we have considered that truth tables are equal means we can say both are equal. In other words, how we can determine is by performing by implication. Then we could able to say if we could able to get a tautology, then we can say both as equivalent, logically equivalent. Clear? Yes.
Yes, sir. Clear.
Yeah. Right. Thank